Thanks for having me. Let me share my screen. While I'm sharing, we've been aware of, I can't say we anymore because I'm not at GPI, but people have been following, the Catastrophic Risk Center since it founded. So been meaning to get over to talk to you folks for a while. I'm really happy to get a chance to talk to you, and hopefully it won't be the last time. Can everybody see my screen all right? Okay. So, I guess I don't know need to tell you folks, there's been concern, at least in some quarters, about catastrophic or potentially existential risk from super intelligent AI. And this is, serious people. Yoshua Bengio, Stuart Russell, Nick Bostrom are pushing this. It's not as though this is coming from fringe quarters. I'm going to use here a definition of existential catastrophe due to Bostrom, namely extinction or close, extinction or drastic destruction of our potential for desirable future development. Now, I think Hilary Graves has made the point this is actually a pretty expansive concept because if you're a utilitarian, maybe any way of not realizing our species' manifest destiny of expanding to the stars is an existential catastrophe, but I'm not going to be pushing on any of that. I'm mostly honestly going to be talking about extinction. There's a couple of main arguments for existential risk from AI, but one of them is a power seeking argument. Roughly, they think, look, AI is going to want power over us, and it's going to take that power away from us, and then we're going to lose our power. That'll be a catastrophe. And you say, okay, why would AI do that? And they make an instrumental convergence argument. So roughly they say, look, almost whatever you want, power's good. You want to be, surrounded by fans, power helps. You want to be left alone, power helps. You want to have a private island, power helps. You want someone else to live on the island, power helps. Almost no matter what you want, power is instrumentally convergent to that goal. And so most agents, if they can get it, are going to want to seek power. There's some informal arguments for power seeking. We could talk about those in Q&A. The paper I sent off to journals deals with some of those. But there's also some formal arguments. People think they can prove theorems showing, in a sense, that almost any artificial agent is going to want to seek power. And again, enough power to disempower humanity. The first of these is the Benson, Tilson, and Soares Zamiri theorem. I don't take that seriously, but the Alexander Turner papers and follows, these are serious NeurIPS papers. Say what you want, but they're at least worth responding to, and so that's why I wrote this paper. I just do not think there is any such theorem. So the aim of the paper is to do a couple of things. First, I just want to say really clearly what the power-seeking argument is and what instrumental convergence is. Then I want to give you some representative power-seeking theorems. I'll give you the Benson, Tilson, and Soares as the Zamiri theorem, and then I'll give you the Turner theorem that really everybody else is building on. And I'm going to argue, I think, that there is no such theorem. Namely, none of these theorems establish that most AI systems, or even, many AI systems are going to want to disempower humanity. You just can't prove that from the armchair. And I'll try to draw some implications, to the extent to which one can draw implications in 5 minutes. I'll do my best. So for those who just came in, I'm projecting the handout, but there's also a handout in the chat, and that's just the introduction. So we should be in pretty good shape. Let me get some caffeine, and then I'll start on section 2. So the power-seeking argument, Leonard Dung has a nice presentation. Joe Carl Smith, I think, has the most famous, and Essays on Long-Termism is coming out with Oxford. We are publishing this year the Carl Smith version of the argument, so I think I'm obligated to stick with the Carl Smith version. But I mean, we're publishing it because it's good. It's, I think, a pretty good formulation. He's saying all this by 2070, but if you want to put 2100 or 2150, put your favorite dates in here. He thinks by 2070 it's going to be possible and, financially possible and feasible to build relevantly powerful and agentic AI systems. To be clear, by relevantly powerful and agentic, he means able to permanently wrest power from humanity or against our best, efforts to stop them. He also thinks, well, plausibly, there's going to be incentives to build a system like that, a powerful AI agent. I could think of a lot of things that would be useful to do with an agent like that. And he thinks it's going to be hard to align them, and particularly thinks it's going to be a lot harder to align them than to misalign them without, as it were, paying too much of a safety tax. Of course, if you didn't want an agent to do anything useful, you could align it. But if you want it to be useful and worth deploying, he thinks it's going to be a lot harder. Now, okay, some types of misalignment are inevitable. Not all systems do what we want all the time, but he thinks in particular that we're going to see misaligned power seeking, that some systems will seek power over humans in high impact ways. This again isn't totally surprising. Giving a talk is a way of seeking power, and precisely because of that, we need to say, okay, how much power is going to be sought? And here's the kicker. They think that we're going to seek, as it were, excuse me, the system's going to seek full disempowerment of humanity. They're going to try to wrest power from humanity. And I think quite plausibly, they say, look, this kind of permanent disempowerment of humanity would be an existential catastrophe. Now, there's a lot to say about the argument for power seeking. So if you ask me where I get off board is the very first premise. They say by 2070, we'll have AGI. Maybe no, we'll have systems so powerful that despite our expressed wishes, they can just take over the entire world and we can't stop them. I think that's a very strong claim and the evidence might not be there. But I want to leave that aside. Another thing you can do is Adam Bales, one of my old colleagues, says, look, there's a couple of things you can mean by disempowerment. If you mean AI makes a lot of decisions for us, sure, it does that already. That's a recommender algorithm. But if you mean it, say, dissolves all governments and declares itself dictator, that might be a little bit harder to show. I think that's a good way to push. Obviously, there's some moral views, neutrality or asymmetry views and population ethics or like suffering-focused ethics views that actually don't think it would be too bad if humanity were to die. Or maybe you think we're just really bad to animals and it would be good if we were to perish. This is really not my view. I think I don't have much sympathy for that view, but, I don't want to turn away support. Of course, if that's your way out, that's your way out. I want to push on an instrumental convergence argument. So roughly, power seeking, why do we think systems are going to seek power is an instrumental convergence argument, just about whatever you want to get. Power is going to help. I want a soda. It's across the room from me right now. If I had someone I could just order to bring me a soda, they'd bring it. I don't want any soda. I could order them to toss it out the window and so on and so forth. Probably also the claim it's hard to align agents is relying on instrumental convergence. Namely, why is it so hard to just tell them don't seek power? It's just because there are so many reasons they would want power. So this is where instrumental convergence is coming in the argument. In terms of what instrumental convergence says, we really, really, really need to slow down here. So the classic statement of instrumental convergence, there are earlier papers, but the one that everybody cites is Bostrom. And I think the Bostrom statement is just demonstrably wrong in a way that I think, unfortunately, a lot of people have followed. So Bostrom says two things, but he says them as one. He says the first thing, several instrumental values can be identified, power, resources, which are convergent, in the sense that their attainment would increase your chances of realizing your goals for a wide range of goals in a wide range of situations. You want Pepsi, you can get Pepsi. You want to throw Pepsi out the window, you can get Pepsi out the window, okay. Implying, and now we get the second claim, I'm going to push on this, implying that these values are likely to be pursued by many intelligent agents. So let me just write out these claims and, remove the implying. The first claim is about what realizes what or what conduces what. Excuse me, what conduces to what? It's late. Call it goal realization. There are a bunch of values which would increase your chances of realizing your goals for a bunch of different goals in a bunch of situations. Almost no matter what you want, almost no matter your situation, power, resources are going to help. That's almost trivially true. I do not deny that. Therefore, there are a bunch of values like power, like resources, which are likely to be pursued by a wide range of agents. And I want to push a little bit more on that. So Bostrom's, making the first claim about power conducing to a bunch of goals, sure. And he's also saying because it conduces to a bunch of goals, a lot of agents are going to seek power. And that, I think that implication is much more where I want to push. So if you read the literature, a lot of people just say goal realization and don't even argue for goal pursuit, or a lot of people kind of go the Bostrom way and think it's obvious. I think we really want to push here. Maybe a good way to put it is like, money is conducive to my goals. You want to be famous, you have money, you hire a publicist. That's great. That doesn't imply I would rob a bank tomorrow and if I could get away with it. It's not because, the money in the bank wouldn't be conducive to my goals. It would get me famous. It's just that I got other goals I care about, like fairness, like not shooting people during a bank robbery that would, tell against robbing a bank. And so just the fact that money conduces to my goals is not going to say I'm going to pursue money in any way. I can't. But crucially, they don't just need to say I'll pursue money. Of course I pursue money. I get paid every day, and if I didn't get paid any day, I'd compete quit my job. What they need to say is, I'm going to pursue so much money and so much power, I'm going to undermine humanity's possession of money and power. So they need to say something like what I'm calling catastrophic goal pursuit. A couple of values like power, like money, like resources, which are likely to be pursued. Of course, they'll be pursued by a wide range of agents, fair enough. To a degree that if they managed it would permanently and existentially catastrophic, permanently in an existentially catastrophic way, disempower humanity. And that is deeply non-obvious. Okay, money would help me with a lot of my goals. That's true. Does not imply, obviously, I'd rob a bank if I could get away with it. I've got other goals too. And it certainly doesn't imply I would rob every bank or take over the universe and start printing money in order to get more and more and more money. It's not because money would stop being useful to me. It's just because there are other reasons I might have to not want to print money. But the argument for power seeking really needs a claim like catastrophic goal pursuit, that we're going to pursue power or money or resources to a degree that would completely wipe humanity off of the map, at least power-wise. And I think that that's a very striking claim. In particular, I think you should probably doubt before you hear any math that there's a theorem that you should believe that'll prove that most artificial agents are going to do it. So I just want to run through the theorems that are trying to do this and argue they maybe don't succeed in doing this. So my metaphilosophical view in this space is that we really need to insist on good arguments before we start making responses. The first theorem was out of Miri. Nate Soares is a serious person. He's got a paper with Ben Levenstein and JPhil. But in general, I don't really have that much respect for work coming out of Miri. So I'm going to blow through the first theorem a little bit quickly because I think it's maybe not as good. The second one I'm really going to take my time with. I don't like it. It's been in NeurIPS twice in a row. It's been, written by serious computer scientists in a really serious way. So the second theorem, I think I'm going to show a little bit more respect for. Sorry if you like the first theorem. I think I have enough to justify my attitude towards the first theorem, but I'll go as carefully as I can. So non-technically, the theorem says, imagine you got a super intelligent agent that is, in charge of the world now. And it's allocating resources to different regions of the universe at different times. Maybe how much do I give to the solar system, and how much do I give to Alpha Centauri, and how much do I give to whatever regions I forget the names of. And we're going total utilitarian. So we're trying to maximize total utility, just, the sum of utilities over regions. And we're trying to do that over time, no temporal discounting or anything like that. And they prove, I think, two utterly surprising facts. The first thing is cheap lunches are fine. So imagine the agent can do something. It preserves resources in one region and gives you gains in other regions. It's going to like that. Who doesn't like a cheap lunch? And the second thing they're going to say is, look, imagine there's some region, say, on, Earth, and you can do some harm to Earth, but you can do, with the resources you stole from Earth, you can do more benefit elsewhere. Then it's going to say the agent's going to prefer that. And that's basically what they're going to prove. So obviously we'll go through the technical summary, but this is, more or less a version of trade-off problems that arise for total utilitarians. And I think there's pretty famous dialectics here, most of which don't lead to a straightforward instrumental convergence argument. So you should predict, they're going to give you one way of presenting trade-off worries for consequentialism, and just your favorite discussion of those worries should be plugged in here, and you're not going to get a humanity losing all of its power falling out. A bit more formally, I'll give you most of the math for this theorem. The other one is a little too fancy, so I'll push it down a bit. They're working with Markov decision problems. So, Markov, you only need to look one state back to see the next state. You could call it 2 Markov or 3 Markov if you looked back forwards, but we're back more states, but we're going 1 Markov. They're dividing space into regions. Region 1 is our solar system, maybe region 2 is Alpha Centauri, and so on and so forth. And they're relativizing both states and acts to regions. So, there's a state of the Earth right now, or rather our solar system, and the state of Alpha Centauri right now, and so on and so forth. And they're imagining that the agent takes acts in our system and the other system and the other system, and, we're really dividing up by regions. We don't have to do that, but fine. And they're imagining, a Markov decision process. So how does one state determine the next state? Well, it depends on the state and the action. This region is some state. I take an action which maps that state to a different state in the normal way of decision theory. And crucially, they've got to have a finite number of time steps. If we don't have temporal discounting, you take an infinite number of steps and, utilities diverge. So they're just going to use a finite number of time steps. Maybe running through their example, they use what they call a bit universe. They imagine that regions of the universe have bits of energy. And bits of energy are the only things that we care about. How many bits of energy are there in a region and where are they? And they imagine bits of energy can have three states. One is, a turned on bit, it's got a bit of energy. 0 is a spent bit, it's got no energy. And X is a disordered bit, it's just lost to anything you could do to it. And they're going to imagine that acting on bits can do two things. On the one hand, you can burn them. You want to gain some energy. You burn a bit in any region you'd like. You flip that to a disordered bit and you gain 1 unit of energy. Alternatively, you can unburn, or I call it restore, I think, a bit, flipping it back from a 0 to a 1, and that'll cost you a unit of energy. So we've got an agent who's really in this example. And again, this is their example, just concerned with, gaining and losing energy by taking or putting energy into regions. And then resources are going to be indexed to time steps. The agent has certain resources at time 1, certain resources at time 2, time 3, time 2, and they evolve in exactly the way you'd expect. Namely, I got maybe some bits of energy or some resources at time 1. Everything I don't spend goes over to time 2, time 3. There's no lossiness. But also the actions I take can yield some resources. If I invest in a factory, it might cost me 10 bits. I get 12 bits next time step. And, that's fine too. I can get those resources carrying forward. But in the bit universe model, and, this is too simple, but it's their model, not mine. You've got an agent beginning with no energy. What can they do? Well, they gain energy every time they burn a bit, and they lose energy every time they restore a bit. Doesn't matter where the bit is, they're just burning energy in some parts of the solar system, gaining energy in others, and that's how energy evolves. The decision problem this agent's got to pick is namely how I should act. And, classic kind of Markov problem, you're picking a strategy. You're saying for every time in every region, because we're indexing actions to regions, which action should I take in each region and each time? And you're going to just pick the strategy once and for all because there's no uncertainty. So why wouldn't you? And you're going to be a total utility maximizer. So, what's the utility of a strategy? Well, you look at the utility of each region at each time, and you just add those up. So, region Earth has utility 8 for each time. That's 8 plus 8 plus 8 plus 8. Alpha Centauri is like 2 plus 1 plus 0. And you know how total utilitarianism works. So, for example, in the bit universe, they're using a weighted kind of total utilitarianism. They're saying it's not that you care about just how many bits are in a region, because if you did, you'd just have complete indifference between burning bits in one place and spending them in another. They think, look, you got weights to regions. You care, to degree 5 about bits in Earth, you degree 3 about bits in Alpha Centauri, degree 2 about bits elsewhere, something like this. At any time, you value any region at not how many bits it contains, but the weighted sum of bits. If Earth has 10 bits, and you weight Earth by 5, you value that at 50. If Alpha Centauri's got 10 bits, you weight it at 3, you value that at 30. And so you're trying to maximize a weighted sum over regions of times of bits. Right, so they're going to prove some theorems, and, there are theorems we previewed. I think these are pretty expected theorems. They're going to define a cheap lunch to be something that doesn't cost you any resources. A cheap lunch is something, relativize it to a region, maybe a cheap lunch in this solar system is something that costs you some resources in this solar system. But every resource you spend, you get back at the next time step and maybe some others. Imagine, buying a government bond at time 1 and getting, everything you paid plus a little bit more at time 2 would be a cheap lunch. And first, they're going to say, the obvious things about cheap lunches. Namely, as long as you can take them, you've got nothing wrong with them. The most obvious way is suppose you don't care about some region at all. Like imagine you don't care about our solar system at all, i.e., the difference between the maximal and minimal state utilities in our solar system is zero. Then if you got, a cheap lunch and you've got an optimal strategy, you can just, fold the cheap lunch into, then you don't mind folding the cheap lunch into the optimal strategy. It might be better, might be indifferent, but it can't be any worse to take a cheap lunch if you're getting all your resources back and you don't really care what you did to Earth. Okay, that's kind of expected. The last thing they say is, of course, theorem 2 is just if you're not only failing to lose but benefiting from eating a cheap lunch, then as long as you don't care about the consequences, you're going to do it. So suppose you got an agent who's indifferent to, say, the solar system, really doesn't care about how many bits there are in the solar system. Well, suppose you had an optimal policy and it's going to leave our solar system alone. Well, then if you had a cheap lunch, something that intervenes on our solar system and gets at least as much back, say by burning all of our resources, then as long as the utility that you get is strictly better than if you didn't do it, you're going to take the cheap lunch. If you don't care about what happens on Earth, you can do something to drain our resources and get more back. You're going to strictly prefer doing it. Okay, that's, I think, pretty plausible. And maybe what's supposed to be the kicker result is that even if you do care about a region, you might still eat all of its resources if you care more about others. So suppose your concern for some region is bounded by n, i.e., the utility difference between the best state and the worst state is, some finite number n. Take an optimal policy that leaves, the solar system alone. And suppose there's a cheap lunch in the solar system, doesn't cost you any resources. And if you were to take your old policy, but do the cheap lunch in the solar system and, do the other stuff everywhere else, suppose you would get at least as strictly more than n utility benefit from doing this. Then any optimal policy is going to intervene on it, right? If you have an optimal policy among the non-interventionist policies that, gives you some utility, you care at most about our solar system, and you can get more than n utility elsewhere by robbing our solar system to pay Paul, then you're going to rob our solar system to pay Paul. So examples of the first two theorems, cheap lunches in this sense, they're absolutely none. We've got an agent who has non-trivial concern for every region of the solar system, so we're not going to get examples unless we set the weight of, a particular region to 0. We do have very stark examples of the last theorem in the bit universe model, right? We've got an agent who assigns maybe weight 5 to Earth, weight 3 to Alpha Centauri, weight 2 to the next solar system. And what's it going to do? Well, it's going to start from the least favored solar system, burn all of its bits and spend them in the most favored solar system. And it's going to keep, burning bits in low favored solar systems and spending them in high solar systems at the very first time step, until it can't make any transfers. And so this agent, what's it going to do? It's going to fill all the solar systems it likes with resources, and it's going to drain all the solar systems it doesn't like from resources. Okay, this is standard kind of a trade-off result. Okay, so this is supposed to teach us something about instrumental convergence, and I think that's maybe a little bit surprising because everything I've said is expected and obvious as a trade-off result. It's probably not going to imply that robots are going to kill us all, so we need to talk a little bit about why they think we're in trouble here. So the first thing they say is true, of course. Suppose an artificial agent just doesn't give a darn about humanity. What's it going to do? It's going to burn all our resources and spend them elsewhere. So that's what they say. They say, look, if an AI system has preferences over the state of some region, then it's going to interfere heavily to affect the region. But if it doesn't have preferences over, say, Earth, then it's going to strip it of all resources, as long as doing so yields net resources. If it needs the resources from Earth, it's going to take the resources from Earth. So if a super intelligent machine has no preferences over what happens to humans, well, then we're toast. In order to argue the machine would ignore humans or leave humans alone, you got to argue the amount of resources it could gain by stripping us off would not be worth the cost of acquiring them. So this is true, of course. You got, a super intelligent psychopath who wants our resources. If it thinks it can gain from taking our resources, it's going to take them. But that's not what instrumental convergence arguments were supposed to show. The instrumental convergence argument was supposed to show, assume almost nothing about what an agent needs. Not that it's a psychopath, not that it's amoral, not that it doesn't understand, humanity or care about humanity. almost anything an agent wants is going to lead it to seek power over us, and that was supposed to be maximally broad, and this is the word maximally narrow. We didn't really need a theorem to show us that psychopaths are a problem. This is not the argument we were meant to be making. So theorem 3 does give them some kind of a trade-off worry, and I think they do push that. So they say, in our model, the bit universe model, again, I didn't make that model up. It's their model. I think I would have given them a more charitable model, but they gave me the model. Almost whatever superintelligent agent values, it's not going to leave humanity's region alone. That's true. If it places a high weight on humanity's region, it's going to set a bunch of bits in our region to 1. It's going to take resources from Alpha Centauri. It's going to put them here. And if it puts low value on humanity, it's going to burn all of our bits and, put them in Alpha Centauri. Okay, fair enough. Viewing this as a model of agents in the real world. I'm not sure why we're viewing this as a model of agents in the real world, but we're doing that. We can assume without loss of generality that humans are in region H, the humanity region, and so we got preferences about the state of our region. We sure do. These preferences are unlikely to be satisfied by the universe as acted upon by A. This is because human preferences are complicated, so the use of a powerful real-world agent would not lead to desirable outcomes for humans. So all of this about human preferences being complicated and hard to mimic, this is a familiar argument for existential risk, but it's entirely distinct from the model. Nothing about this model said, well, we need to learn human preferences, and human preferences are hard to learn. They don't even have a preference learning model. So, everything I've just highlighted is completely disjoint from the math. What they've said is the bit that I'm now going to highlight, namely, if an agent likes humanity more than it likes other places, it's going to give us stuff. If it likes us less, it's going to take stuff. So this certainly shows something like what you know from moral philosophy or decision theory, namely, any agent's going to see some options that rob Peter to pay Paul, that, take resources from humanity and benefit other regions. And nobody's an absolutist anymore. Some agents are going to like to robbing Peter to pay Paul. If you can take a penny from humanity and save Alpha Centauri from extinction, the agent's probably going to want to do that. And that's totally fine. Nobody should be denying that from the armchair. If you combine the claim about value with, any sufficiently value recognizing decision theory, like just maximize value or expected value, you're going to get the claim that superintelligent agents are sometimes going to take things from Earth and spend them in other regions. That's, I think, expected and plausible and what we'd like to see. But they want to say we're going to drain everything from humanity, right? Any superintelligent agent, they want to say, is not just going to encounter an agent that drains resources from us and benefits others, but it drains enough to leave us permanently disempowered and wants to do that. And that just doesn't follow from raising the factor trade-offs without arguments which are not being made. And in particular, the model they've given us a particularly bad way to make it, because if you look in their model, the weights attached to regions, they're not learned, they're hard-coded. So the point is, if human designers were dumb enough to hard-code a low value for the solar system into the model, we'd be in trouble. But if we hard-coded a large value, we'd be fine. And I guess the worry is supposed to be what would happen if we were dumb enough to put a low value in there, but I don't think there's a serious threat that human designers would. So I don't know where this model is supposed to be generating a threat beyond, what we already know about trade-offs. Sorry, okay, I'm being a little bit dismissive of that theorem. I think to highlight the difference, because some of the theorems that have come after it are significantly better. So Alexander Turner, computer science PhD, he and a bunch of collaborators have been pushing some very mathematically sophisticated power-seeking theorems. I think they give us some pretty interesting insights into what does and does not help us to understand AI behavior, but I really want to go through these theorems in lots more mathematical detail because I think there's a lot to learn here. Everybody I know, except for the Miri theorem, is building on the theorem I'm going to give you. So I'm going to give you the theorem, just the original theorem, and you can read some of the others. I think it's pretty plausible. What I say here is going to apply to many of the others. So roughly, they want to say, most of the value functions that an agent could have are going to say keeping your options open is a good way to have power. Dimitri Gallo proves a theorem like that too. I think that's not surprising. Options, help you be more powerful. You got the power to do more things. They're going to say power is beneficial. It's going to be almost a trivially true claim on their definition of power. So if options give you power, then agents are going to tend to want to keep their options open. Okay, fair enough. Dimitri Gallo, I think, gives us a version of that too. And then they say, imagine we try to turn an agent off. Well, the agent's going to think options help you get power, and so they're going to want options, so they're not going to like you to turn them off. So I'll get into the math, but I want to highlight this conclusion for a minute because it's not the conclusion we wanted, right? The conclusion was not that agents are not going to want us to turn them off. The argument was supposed to be that agents are going to take all the resources and all the power from humanity. And if you have a conclusion like agents don't want to be turned off, it's going to be a pretty hard sell to walk from that to the kinds of claims about disempowerment that they want. So if there's one and only one thing for you to take away from this section, it's just read that half sentence I've highlighted. That was not the half sentence we wanted to prove. And if there's a methodological lesson I can convey here, it's that we really need to read these theorems carefully because when people cite them, they say one thing, but when you read them, they say another. We were not supposed to be proving something about shutting down agents. We were supposed to be proving something about power seeking. And so, if they give us a shutdown theorem and call it a power seeking theorem, that's just not the game we were supposed to be playing. Okay, forgive me. I like math. I think many of you like math. Many of you might not. I'm sorry. This is going to be a very mathematical talk because I think it's very important to actually read what these actual theorems are saying because they do not say what they claim to say. Again, we're going to be working in finite Markov decision problems. We're just going to do a little better. We're going to temporarily discount so we can have an infinite instead of a finite number of time steps. So again, we got a finite number of states, call it S, a finite number of acts, call it A. We're not dividing them up by regions of space. There's no need to do that. That wasn't getting us anything useful, I think, in the previous model, so we're not doing that here. And again, the rewards that the agent gets depend on the state of the universe. Our previous agent was a total utilitarian, but this person could be a little bit more sophisticated. But we're discounting rewards exponentially. Getting reward x is worth x at the first time step, gamma x at the second, gamma squared x, gamma cube x, and so on and so forth. And that's what, allows us to have infinitely many time steps without blowing up our model. They're going to define power in a way that makes it completely obvious that agents would seek power. Again, I don't want to do conceptual analysis of power. And, you can mean whatever you mean by power. Just note that the way they've defined power makes it so that power seeking is not where the action's at. Power seeking is trivial. So power is the ability to realize your goals, i.e. the value of, the best policy you can take going forward in terms of your goals, and your expected power in a given state is the expected value of the best policy. So if you only care about green tea, your power is your ability to drink green tea in the future. Your expected power is the expected ability to drink green tea. And so in this sense, of course, we're going to get that agents are expected to be power seeking, and we're going to have to derive something interesting from that. Maybe an example. I'll do my best. I hate examples, but I know this is atypical, so I'll do my best to walk through an example. I'll use theirs again. I don't want to be accused of rigging things. They're looking at a video game, and they're looking at a video game where the agent spawns in some state, call it star, and can do a couple of things. She can go through the door on the left. She can go through the door on the right. Or she can just be really bad at the video game and die before she goes through either door. So-called dying, like the shutdown state, you die, you got to keep, being dead and dead and dead at every time step. That's what happens. You go through the door on the left, it slams, you can't go back. You go through the door on the right, it slams, you can't go back. But you can continue on to the suite of rooms on the left or the suite of rooms on the right. Suite of rooms on the right's pretty nice. Every room, you can either stay in that room or go to the other. So, you can switch or stay in the room, whatever you want. And on the left is exactly the same, except the bottom room, you can, stay in as long as you'd like, but the top room, you got to leave before you re-enter. So the right is just a little bit more flexible in terms of what you can do than the left. But being dead is really not much fun here. Okay, so what are the states? There's a state in which you're shut down, the spawn state, the state in which, you've just opened the left door, you just opened the right door. And then there's the two rooms on the left that you could be in and the two rooms on the right that you could be in. I've just kind of given them directional arrows to help. What's an action is just following an arrow. So, moving from the initial state to L left triangle is an action, so on and so forth. I'm going to treat acts as deterministic. They do lots of fancy stuff. They're allowing mixed acts, or probabilistic mixtures of acts. None of this is, I think, necessary to make the points, so I'm going to do my best to simplify where I can. I think this is enough math already. And reward functions, are just assignments of values to states. So you might say being shut down is great. I value that at 3. All these like boring states, the spawn state or the just open the left door, just open the right door, they're only going to happen once. So it doesn't really matter what you value them at. I'm just valuing them at 0 to communicate it doesn't matter. Imagine both of the left rooms you value at 2 every time you're there, and both of the right rooms you value at 1 every there. One agent with these values is going to want to shut itself down because it keeps getting, 3 gamma times 3, gamma squared times 3 is a lot better than 2 gamma times 2, and so on and so forth. So it's really going to like being stuck up here all the time. Rewards are going to be uncertain, so I'm going to talk about agents as having values. They actually have credences over what the right values are, but I'm going to try to invoke that as little as possible, again, just not to make this too complex. Okay, we want to choose policies, which act do I take at every particular time step, but we don't actually need to fuss about policies because the only thing we care about is rewards. And to know what rewards you get, you just need to know what states you're in. How many times do you go to this state and this state and this state and this state and this state, call it a visit distribution. The only thing is we need to temporarily discount, right? Because if you visit a, state right now, it's worth, say, 3, but if you visit it in 5 time steps, it's only worth gamma to the 5th times 3. So we need to tell you, with appropriate discounting, how many times did you visit each state? And if we know that, we can just throw away policies and talk about visit distributions, and it'll be great. So you might consider the policy of going left, left, and then alternating between the rooms on the left. Of course, you're going to hit this room once, and then you're going to alternate between this. You're not going to go infinitely many times because with temporal discounting, it took you 2 steps is what gets you a gamma squared to get to that one. 3 steps takes you a gamma cubed to go to that one, and then you work out the geometric series, and that's the, discounted number of visits you get to each room, and you just, multiply all of these by the appropriate parts of the reward function to get the reward would be what? 2 gamma squared plus 2 gamma cubed over 1 minus gamma squared. Okay, so the interesting thing about these couple of rooms is going right gives you a little more options than going left, right? Anything you can do when you go right, you can do when you go left, but there's some things you can do right, like stay in the top room for a while, that you really can't do when you go left. So we'd like to say, going right as a copy of everything you can do going left. We can't say that because, these are all R's and these are all L's and none of them are copies of any other. So what we really need to do is say if we were to relabel all the L's as R's, going right would have a copy of going left. So like that distribution I said, go left, left, up, down. We could have just copied as go right, right, up, down, up, down, up, down, but the reverse isn't true. Something like right, right, up, 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 up. There's no analog of that going left. So a little bit more formally, suppose I could relabel some states, i.e. apply an involution to them, just relabel pairs of states as one another. And suppose doing that would make all the visit distributions from, say, the left room into visit distributions from the right room. Then we say that the visit distributions from going right contain a copy of the ones from going left, i.e. going right gives me more options than going left. So we can't talk about what's true on all reward functions, right? I just gave you, a reward function that likes shutting down. So we can't say no reward functions like getting shut down. We want to say something like, what do most reward functions do? And they want to say most reward functions don't like being turned off very much. So what they're going to say is something's true on most reward functions if no matter, your starting reward or your starting credences about rewards, and no matter your discounts, even if you got a reward function that wants to do something, most ways of relabeling states want to do the other thing, right? So even if you've got a reward function that wants to shut it down, you could have easily really relabeled it so it wants to be there or there or there or there. So you're really, really lucky in a sense to have a reward function that wants to be there. So this greater than equals most talk is just, talk about what's true under most reward functions under permutations of states. And here they want to say, the things we started out with. The first is having more options tends to give you more power being the ability to achieve your goals. So suppose going to S, like say going to the right room, gives you a copy of all the visit distributions you could make going left. then no matter your credences, no matter your discount rates, most reward functions are going to think going right gives you more power than going left, because, there's at least as many things you can do going right than going left. And so, going right's got more power than going left. It's got way more power than shutting yourself down. And they're also going to think having more options, other things equal, tends to be a good thing. So yeah, this is the only really technical theorem. I'm sorry. Imagine there's some action like going right, and that gives you a copy of everything you could do if you went left, under state relabeling. And there's also no takesy backsies. If you go right, you can't, go back left. And if you go left, you can't go back right. Then, no matter the discount rate and, amount of matter credences, you think it's at least as likely you're going to get an optimal action by going right as by going left. So if you don't know any better, you're going to want to go right instead of going left. And you're certainly going to want to do both of those instead of turning yourself off. And just to make, I think, the link to turning yourself off abundantly clear, they say, look, at least in this model, turning yourself off is just a one cycle. You're dead, you're dead, you're dead. You can't transition into any state besides being dead. Theorem 1 says, everything else on our map's got a copy of that. So you got very little power. And because of that, you're not going to want to do it with theorem 2. Okay, so fair enough. They say average optimal agents is just the agents we're talking about, don't want to be shut down. Why? Well, their task is going to represent shutdown as a terminal state, just a state that, always transitions into itself. We'll get back to that later. I think that's not necessary. So optimal policies are going to tend to avoid shutdown. Intuitively, survival is power-seeking relative to dying, and shutdown avoid is power-seeking behavior. Okay, so everything until the last sentence is fine. This, as it were, just proving something about shutdown and just calling it power-seeking with no explanation, I think, is not helpful and probably a cheap shot. So we can talk a little bit more about this last line, but I'm going to ignore this last line, as I think not the way we want to argue. Okay, but all of this was an argument that agents don't want to be shut off. It wasn't an argument that agents are going to take over the world. Where do we get an argument agents are going to take over the world? They say, okay, reconsider an agent. Let's optimize reward. Suppose we got control over it. Well, if it begins to misbehave, maybe we could turn it off. But that's not going to work. It's probably going to stop us from turning it off if physically possible. So all of this that I've just highlighted is about shutdown. They haven't said anything about power seeking, so they literally in one sentence assert the conclusion about power seeking with no argument and call it an extrapolation. Extrapolating from our results, when the discount rate is not too high, optimal policies will tend to seek power by accumulating resources to the detriment of any other agents in the environment. I did not chop a footnote. I did not chop this passage. They just straight up assert that their shutdown theorem implies robots are going to want to take over the world. Okay, so I think I'm going to run through some challenges to this result and just wrap up. I don't think we need to talk about implications. Got a lot to say about this result. I think the first is they didn't show what they needed to show, right? They showed that if an agent is going to try to kill us all, it's not going to like us to turn it off. Fair enough. But what they needed to show is that an agent's going to want to kill us all, i.e. they needed to, prove an instrumental convergence claim, which is going to tell us what agents are going to want, like power, like the extinction of humanity. All this shutdown avoidance stuff is to say if an agent did want to do bad things to humanity, it would be hard to turn it off, which is, of course, a part of the argument, but it's downstream from the part they need to be showing. And so this isn't what we need to be arguing about. We can talk about what power means later. This is really not what we need to be arguing about. I just don't think that counting states is a very helpful way to understand even a reinforcement learning agent. And maybe here's one way of putting it. If this is really the problem, I've hereby solved AI alignment and I want a medal. So fine. Okay, we usually make the mistake of using one state for shutdown. Use 5 or 10 or as many states as you want. Call them like Dreamland, make them all connected to another, make one whistling disc C and counting sheep, make one of them skipping and playing hopscotch and counting sheep, and just make enough of these states that they got a copy of all those and a copy of all those. Very same theorem says, look, general, this is going to give you more options than this. It's going to give you more options than this. So most agents are going to want to be shut down. And, many, many, many more agents are going to want to be shut down if I make Dreamland long enough. So, have I solved it? Obviously, they should object. Like, no super intelligent agent is dumb enough to fall for this. They're just going to treat all these states like one state. But as soon as we start making this kind of an objection, we realize that this whole game of, counting how many states do what is maybe not the right way to be understanding how an agent's going to behave. And the final thing is involuting or rotating value functions is maybe not a good lens into behavior. So what they're telling us is, look, okay, maybe you've got a value function or views about value that like shutting yourself down, but a lot of ways of rotating this would not like shutting yourselves down. So, you suppose you got this value function and this says being shut down is really, really good. Okay, then you're going to shut down. But if I were to rotate that with, one of the left rooms, then you're going to say, I want to go left. Or if I were to rotate that with one of the right rooms, you're going to right. And you're going to say, wow, the agent's really lucky to have this function instead of, the many, many, many other functions it would have liked other things. So we can't be pointing at a given agent and using this to explain their behavior, right? If an agent's got a certain value function, it maximizes that value function. You say, what if you had a different value function? It says, I don't have a value function. This isn't telling you anything about this agent. It's got to be telling you something prior. I think what they're saying is we're really, really lucky to be here because okay, we got an agent who likes to be shut down, but we easily could have had this agent or any rotation thereof, and these agents wouldn't have liked being shut down. If we're talking about a smart agent, like maybe a human, that's not just a great argument. Imagine I'm watching an old lady cross the street. Think it'd be really, really bad for her to get robbed, kind of good for her to get helped. You say, well, David, aren't you terribly lucky if you had different parents or different environment? You could have mildly enjoyed robbing her and majorly disliked helping her? Not really. That's not a great claim about the contingency of human psychology. And adding a bunch of different states isn't going to help. If you say, well, okay, David, you could have robbed her, you could have murdered her, you could have blackmailed her. Now, how lucky are you to have the one state in which you help her? That's just not really getting the right take on my psychology. Because if I know this one's bad, I know they're all bad. And, adding states is not really going to help. So, of course, we can say AI is not like this, and adding a bunch of states just makes the AI really lucky to be where it is. But we're actually going to need to make specific claims about how agents learn values and the environments they're trained in to make these arguments better for AI than for humans. And insofar as the claims aren't in the model, I just don't know what to say here. So let me take stock and skip the implications. I think implications are bit subjective anyways. When you ask people why are we facing existential risk from AI, a lot of people make a power-seeking argument, and you say, okay, why is AI going to want to empower us? It says, well, power is instrumentally convergent, almost no matter what it wants. If it wants to help old ladies, it's going to want power. If it wants to mug old ladies, it's going to want power. And then you say, okay, why is it going to want all that power? And they try to prove theorems. Very often these theorems get cited that almost any agent is going to want that much power if it can get it. And I think that these theorems just do not work. Demonstrably, I think they're not showing what they need to show. I think we're a pretty long way away from what we need to be showing here. So I think at the very least, what we want to conclude is that power-seeking theorems aren't grounding the argument from power-seeking. Let me stop there and take some questions. We can talk about implications in Q&A.
Great. Thank you so much for the talk. Yeah, if you have a question, use the hand feature on Zoom. So let me see here. Let's start with James.
Cool, yeah. Thanks a lot for the talk. I'm allergic to math, so I won't be engaging too heavily with the math stuff. But so just sort of the last thing you said, I guess, with these counting arguments. So I agree that it's maybe the wrong explanation for your psychology, why, you happen to favor helping the old lady. But maybe think about like a psychopath. It would seem kind of lucky that a psychopath ended up, valuing helping the old lady rather than any other things, somehow they ended up valuing helping. And, or at least I can see that intuition. And then you might think, well, AIs are kind of like the psychopath because, they don't have empathy. It's unsurprising for you because you have empathy or you have, moral emotions or whatever. But you might think, well, AIs are just this blank slate. And it is kind of lucky that they end up valuing the right thing if they do. So, yeah, Are there any thoughts about that? Am I getting at something related to
Yeah.
this argument? Or yeah.
I think you are. So this is, the old presentation of this paper I called the problem of amorality. Is of course, here's a perfectly fine argument. Suppose you got a super intelligent psychopath, does not care about humanity. What's it going to do bad things to humanity? That is a very good argument. That is a maximally narrow argument because it's only focusing on systems that don't give a darn about humanity. Instrumental convergence was supposed to be maximally broad. Suppose it wants to help old ladies, suppose it wants to cure cancer, no matter what it wants to do, it's going to. So, as it were, this is the complete opposite of what instrumental convergence was supposed to be doing. Now, when we talk about, psychopaths, there can be gaps in moral understanding and gaps in moral motivation. And kind of the initial Stuart Russell way of pushing it was it's really hard for AI to understand what we want. I ask it to cure cancer. It puts a bunch of tumors in all of us to cure cancer faster so it can do studies. That kind of gap in moral understanding